So last time we just finished up talking about centrifugal microfluidic devices, centrifugal pumps and valves. So we're going to continue the discussion on the different types of dynamic micropumps. So we mentioned centrifugal micropumps. We'll talk about some of the remaining ones today. So again, the difference between displacement and dynamic micropumps, displacement micropumps is actually a moving part, usually some type of moving diaphragm that's causing the fluid to move through the channel. In the case of dynamic micropumps, there's some type of energy being added to the fluid itself. In some cases, as we saw last time, centrifugal energy is momentum energy being added by spinning the disc that contains the fluidic channels. We'll also talk about mechanical energy, magnetic energy, electrical energy, and so on. These are different ways that you can pump fluids through a channel. So I'm going to move through this relatively quickly because I would like to really get into the separations module today. So we'll start off by talking about acoustic streaming micropumps. This was a paper that was published in 2009. Similar ideas have been proposed. One of them we saw in the mixer chapter. When we said if you take an air bubble, you trap it in the channel, and then you apply an acoustic vibration to the entire system, you will get something called acoustic streaming that occurs at the air-water interface. This happens because the difference in mechanical impedance due to the difference in densities. Air is a very, air has a very low density. It's compared to liquid. It's about 1,000 times difference, 3 orders of magnitude. So when you vibrate the entire system, these acoustic vibrations are focused at areas where there's a large difference in mechanical impedance. So that's the reason why you have these trapped air bubbles here. So this pump, they call a lateral cavity acoustic transducer. It consists of the main channel going through the middle here, and then you have these lateral transducers on the side, and these lateral channels are filled with this air bubble. Okay, the acoustic energy comes from the external piezoelectric buzzer, as was the case with the mixer that we saw. And it's coupled to the device with an ultrasonic gel. Now, if you just push the buzzer into the device, you won't get as good coupling. The ultrasonic gel is, it's similar to what's used when you're monitoring pregnancies. It's an acoustically matched gel that prevents some of the acoustic reflections from going back into the transducer itself. So the vibrations go into the chip with a higher efficiency. So when you have a bunch of these acoustic transducers together, remember the mixer just consists of one of those bubbles. In this case, you have these multiple bubbles that are flanking the sides of the channel. When you add this acoustic field into it, you end up with streaming at this interface, but due to the geometry, there is more flow going in the forward direction than there is flow going to the backwards direction. And that has to do with the location of the bubble in the channel with respect to the remainder parts of the channel. There's only one of these streamlines goes into the bubble while multiple streamlines come out of it. As a result, you get a net flow going forward. And the flow rates are 250 nanoliters per minute at 40 volts and then 5 nanoliters per minute at 5 volts. So the advantage of this type of thing is that, particularly with the 5-volt thing, 5 volts means you can power it from your cell phone. Okay, and that's where they were going with this. The lower the voltages your device has, the more portable it becomes. Okay, at around 5 volts, you can get it into you can power it through USB. So that's one of the advantages of this type of pump. The frequency is not a problem because piezoelectric buzzers they can go at hundreds of kilohertz, even megahertz if necessary. The potential drawbacks of this technique is that it's relatively low pressure. This type of acoustic streaming, it can provide flow rate only if you don't have too much back pressure in the system. Secondly, the bubbles can dissolve, pumps cannot be individually addressed. Those are all some potential drawbacks, but still it's a very nice technology that you can get a pump just by vibrating the entire system. This is a process flow on how that was made. So the buzzer is actually placed down here and the ultrasound gel is placed in the middle here. Notice that the piezoelectric device is just placed outside the chip rather than inside the chip. If you have microfabricated materials like PZT inside the chip, that would increase the cost. Okay, so by having the buzzer externally, it's a more of a modular type approach to doing this. If we talk a little bit more now about the electrical and magnetic pumps, so these classes of pumps use electrical or magnetic fields to move fluids through the chip. Some of the obvious advantages is that you don't have moving parts, which can fail due to fatigue. And you can also have simpler devices in the sense that electrodes are fairly easy to fabricate. If you want to get an electric field inside your microfluidic channel, you can fabricate electrodes in there. It does increase the cost of your device a little bit, but as we said, it depends what the value added is to this device. If your device can do pumping with just a set of electrodes on there and not much else, that actually it makes it economically viable. We'll talk more about this in the next module when we talk about chemical separations. So some of the disadvantages is that they often require conductive or magnetic fluids. They depend on surface charge interactions, so the channel material actually has to be made with the correct material. Often glass, for example, is used for electro-osmotic flows. And then sometimes if you use a large electric field, this can cause issues with bubble generation. Okay, if you take two electrodes, you put them in a solution, and you put large voltages across there, you'll get currents going through there, and you'll generate bubbles. It's called electrolysis. So obviously, we don't want to do that because bubbles can cause a lot of issues in microfluidic devices. So this chart shows a summary of some of the different types of electrokinetic pumping methods. Electrohydrodynamic mechanisms add some type of electrical energy to the fluid. Electro-osmotic pumps rely on the interaction of the fluid with the channel walls. So we'll talk about each one of these, and then we'll mention a little bit about magnetohydrodynamic pumps as well. So this is a slide about the electrical double layer. This is a very fundamental concept that is important for electrical pumping, and it's going to be equally or more important in the next module for chemical separations. So this phenomena is something that occurs when you have a liquid that's in contact with a solid. Okay, for example, the example that is often given is something like glass or silicon. These materials, they acquire a negative surface charge when they're wetted with water. So let's say you have a glass microchannel or a silicon microchannel. When you fill that channel with a liquid, with your sample, you're going to generate something called an electrical double layer. This can be used for pumping. It can also be used in chemical separations. So the electrical double layer is called the Debye layer. So what happens is that, for example, with silicon, silicon has these OH groups hanging off the end of it, and when it's wetted with water, those the hydrogen atoms become removed, and that leaves this negatively charged oxygen on the end group here. So within the glass, you have the glass surface becomes negatively charged. Okay, so to get an electrical double layer, it's very important that you choose the right material and you choose the right liquids. So as a result, what happens is if you have a bunch of negative charges here, you can imagine that all the positive charges in the fluid are going to be attracted to that. Coulombic interactions, right? So the interesting thing that happens is that suppose your liquid is some type of saline solution or something that has positive and negative ions in it. As a simple example, salt water, right? Salt water has Na plus ions and negative chloride ions. Na plus, Cl negative. Right? So there's some of these positive ions floating around in there. There's some negative ions floating around in there. Because the solid surface has all this negative charge on the surface, these positive ions are actually going to be attracted to the surface, and they'll build up at the surface. So you end up with a charge distribution. Okay, there's actually, if we were to exaggerate this a little more, you'd see that the surface of the liquid will be filled with positive charges, and that's referred to as a stern layer. So you have these positive charges here, and you also have, these are called the counter ions and co-ions. And this graph shows the concentration of the counter ions and the co-ions. Notice that the counter ion concentration increases rapidly, so the counter ions would be, in this case, would be positively charged, the positively charged ions. The concentration of it increases near the surface here. You also have the co-ions. The co-ions would be, in this case, negatively charged. They have the same charge as the solid surface. The co-ions, due to the high concentration of positive ions, these negative ions then get attracted to these positive ions here. So they also have a slightly increased concentration near the surface of the channel. But notice that the surface charge is primarily positive. The counter ion charge density is much larger than the co-ion density. So you have more of these plus charges than you do the negative charges. So whenever you have a whole bunch of positive charges that are aggregated together, you get an electric field. And you get an electrical potential. I'm sure you remember this from physics. If you have a positive charge here, this gives off an electric field. Right, and this electric field is proportional to, or inversely proportional to the distance away from the positive charge. So if you have like a buildup of positive charges here like this, so the negative, you have all these negative charges at the wall, some buildup of positive charges in the fluid. You also have some buildup of negative charges here, because they're attracted to this high concentration of positive charges. And so what ends up happening is that if you were to plot the electric field, the electrostatic potential would go down like this. So y is the distance away from the surface of the wall, and the voltage, or the electrostatic potential, reaches a maximum at the surface, and then it goes down. The voltage is proportional to e to the negative x over lambda d. I'm sorry, e to the negative y. I'll come back to this in the next module. For now, let's just assume a qualitative sort of idea here. Okay, that you have a high concentration of ions near the wall, and as you go away from the wall, the electrical potential drops to neutral. So you'll have like a voltage buildup at the wall. This voltage is referred to as a zeta potential. It depends on the surface properties and the ion density of the liquid. And this distance here, the width of this region, this is the width of the electrical double layer, is given by this equation here. This is the Debye length. Debye length is this is a square root. The square root of this quantity here, epsilon, is the dielectric constant of the liquid. Kt, K is the Boltzmann constant, T is the temperature. On the bottom here we have E squared. This is E is the electron charge constant, 1.6 times 10 to the negative 19. And this portion here is just a simple summation of the ion's valence numbers and the respective ion concentrations. So if an ion, like Na+, for example, Na has, sodium has a single positive charge, right? So then in that case, the Z would be +1. For the chloride ion, Z would be -1. Okay, and N would represent the ion concentration for each one of these guys, which would, in the case of NaCl, it would be equal to each other because Na and Cl you have equal amounts of both. That may not be the case for other types of solutions. Okay, so what you can see here is that the larger ion concentration will reduce the Debye length. Higher salt concentrations will reduce the width of this. So as a result of this electrical double layer, we can use it for pumping. Okay, this is another graph, another picture which shows the basic concept here. It also shows a little bit more detail on the Debye layer. The Debye layer, actually, you can break it up into two, conceptually you can talk about these different sublayers. Okay, you still have this negative region. This is the glass surface that has negative charge on it. The stern layer is all those positive ions that are attracted to the negative ions. So this layer, because it's so close to the wall, it's called the stern layer. It's the immobile layer. Remember, we talked about the no-slip boundary condition, right? So, the things don't move when you're right at the wall. So this region is immobile. They call it the stern layer. Next to it is a diffuse layer. The diffuse layer also has a buildup of positive charges and negative charges. You can see that the concentration of positive charges is larger than the concentration of negative charges. More positive ions here than you have negative ions. Can everyone sort of see that? That's the key to electro-osmotic flow. You have a whole bunch of positive charges here and only 3 negative charges, as you can see in this schematic. So if you were to just put a voltage across the channel, across the length of the channel, these positive charges are going to want to go away from the positive terminal towards the negative terminal, right? So as these ions are pushed from left to right, as they're pushed towards the negative terminal, they're going to pull liquid with it. You can think about each one of those positive charges as sort of like tugging some of the water molecules around it with it, just through drag forces. So you can see this is a very different philosophy on pumping than the conventional way of thinking, where conventional way of thinking is like, you have a peristaltic pump or your diaphragm moving back and forth. In this case, you're actually using electric fields. The ions within the liquid are charged, and you're putting an electric field to move those ions, and when those ions move, they drag some liquid with it. Now, why doesn't this work at the macro scale? It's because this is a surface effect. This buildup of charge here is only happening at the wall of the channel. If you tried doing this in a very large pipe, in principle, you would get some electroosmotic flow near the edges, near the walls, but that's not enough to drag the liquid in the pipe, in the middle of the pipe, with it. But when you're at microscale devices, when the wall is very close, now you have the ability to actually drag the liquid in the middle with it. So what's happening here is that the ions, the velocity is actually being generated by the walls, this flow vector here and this flow vector here, but due to the drag forces, it's actually pulling along the liquid in the middle as well. So as you can imagine, like the key part of this to work is building up these positive charges here. So the surface properties of the channel wall and the properties of the liquid, the ion concentrations in the liquid, play a very important role in electroosmotic flow. So you have to be careful about your material selection, and it only works with certain liquids. EOF depends on the applied electric field, the cross-sectional dimensions of the channel, the surface charge density of the channel wall, and the ion densities and pH of the working fluid. All of these determine the charge distributions, which ultimately develops the flow rate. With electroosmotic flows, typically the flow rates are relatively small, less than 1 microliter per minute. However, you can generate very high pressures, in sometimes even greater than 100 atmospheres. That's a lot. That's a lot. Like 1 atmosphere is 15 psi. This electroosmotic flow could potentially generate like in excess of 1,000 psi. And these are some formulas for DC electroosmotic flow. The velocity U is given by epsilon times the zeta potential. This is what we saw in the previous slide. And then mu is the viscosity. dV dx. So the more voltage you place across there, obviously the larger the voltage is here, the velocity will go up proportionally with the applied voltage. dV dx is delta V, the difference in voltage, divided by dx, which is the length of the channel. So this zeta potential is very important. If you get a large zeta potential, you'll get electroosmotic flow. In materials where the zeta potential is 0, for example, PDMS on its own, the zeta potential will be close to 0, so you won't get very much flow on there. But if you treat the surface of the PDMS with some type of oxygen plasma, then you'll change the zeta potential, and you will be able to get some electroosmotic flow. For a cylindrical capillary, the flow rate is given by the following formula. And the two things I want to point out here is, notice that there's a pressure-driven term, and then there's an electroosmotic flow-driven term. So Q, again, is the flow rate. The flow rate, the volumetric flow rate, so meters cubed per second. There's a pressure-driven term, so this is determined by the difference in pressure between one side and the other side of the channel. This is the stuff we've looked at before. And then this term here is due to electroosmosis. There's a lot of variables here, but it's actually not too complicated. You know, pi, the A is just the radius of the capillary. Epsilon is the dielectric constant of the fluid. You have the zeta potential here again. This is the electric field. The electric field and dV dx is the same thing. To find the electric field, all you have to do is divide the voltage across the channel, the delta V, and divide that by the length of the channel. Then you have the viscosity at the bottom. This function here is something that's equal to 1 if the radius is much smaller than the Debye length, or if the radius is much greater than the Debye length, and it goes to this factor when the radius is very small. So the Debye length can be on the order of, it can be as little as a few nanometers, or it can be hundreds of nanometers, depending on the concentration of the salt solution, and so on. So usually, unless you're working with nanochannels, the dimensions of your channel are going to be larger than the Debye length. So this term here would just be 1. The thing I want to point out in this formula is look at the scaling. We've been talking a lot about geometric scaling in this class. The pressure-driven term, the flow rate due to a pressure gradient, scales as a to the 4th. The electroosmotic term scales as a squared. So which one's going to be more significant at the microscale? A squared, right? Remember, the smaller exponents become more significant at the microscale. The larger exponents become more significant at the larger scale. So this term starts to become more significant when you're working with small dimension capillaries. All right, so there's favorable scaling here. So once you're able to establish electroosmotic flow, controlling that flow is quite simple. All you do is control the voltage that you placed across the length of the channel. All right. So to find the, just a little trick with these formulas. If you want to find the maximum flow rate, you set the delta P equal to 0. So this is if you have no back pressure in the system. And if you want to find the largest amount of pressure gradient, you set Q, you set the flow rate equal to 0. So if you do some math here, you can actually figure out that the maximum pressures in some cases can be greater than 100 atmospheres for some working with certain working liquids. These are some pictures of the different flow profiles you get from electroosmotic versus Poisson flow. I mentioned here that you get the square profile with electroosmotic flow. This is very unique, because with Poisson flow, remember the pressure-driven flow, it was a parabolic flow profile, right? So with parabolic flow profiles, you get dispersion. So suppose you were to inject a sample into your channel. Ideally, we'd like the sample to just stay like a band the way it is. But because Poisson flow has a parabolic flow profile, this sample actually gets distorted and it gets spread out into more of a parabolic shape, and this causes whatever was in the sample to kind of mix with each other. This is called dispersion. You started off with this nice clean stack of chemicals that you put into the channel, and because of this parabolic flow profile, they disperse. And a lot of times in chemical separations, you don't want that. You prefer to keep the chemicals the way that the same way that you inputted them into the microfluidic channel. You'd like to keep their relative positions. So with electroosmotic flow, because it's a square flow profile, the flow velocity everywhere in the channel is the same. Everywhere in the cross section of the channel is the same. These chemicals actually move. These ions move together with one another. I've always found electroosmotic flow interesting from an electrical engineer standpoint because it's pretty much just electromagnetics. Electromagnetics and together with some hydrodynamic phenomena. Now, if you want to manipulate samples with electroosmotic flows, all you have to do is apply voltages between different regions of the channel. So these are some examples where you have a cross structure here. You can't see it in these slides because of these are fluorescent pictures which are normally taken in the dark. But this consists of a channel that goes lengthwise like this, and there's a vertical channel here like this. So what they did here is they have their sample coming in, going through the channel here. So the first thing they do is they place a voltage in the vertical direction. Positive voltage here, negative voltage here, and that causes the sample to just load into this upper channel like this. Then they remove the voltage here and they apply voltage horizontally instead. When they apply the horizontal voltage, you'll notice that a little bit of the sample starts going through this channel here. And this is a technique that's used in microfluidic separations. We'll talk a little bit more about that. The point to be made here is that just by applying voltages at different parts of the chip, you can get flow in whatever direction you want. So from an instrumentation standpoint, it's very simple. You're literally just putting voltages at different places. Now in reality, one of the downsides of electroosmotic flow is that you sometimes require large voltages, tens or hundreds of volts to run liquids through channels. If the channel is long, it could be even larger than that. But compared to macroscale systems, the amount of voltage that you require is not quite as much. Okay, we're going to skip over the AC electroosmotic flow just in the interest of time here. We can talk about electrohydrodynamic pumps. So we moved away from electroosmotic pumps. Electrohydrodynamic pumps rely on adding an electrical energy to the fluid itself. Electroosmosis was applying electric fields to charges in the fluid. Electrohydrodynamic pumps consider the Coulombic interactions as well as multiple other factors that can generate an electric force. So these are all the different electrostatic forces that act on charges in the fluid. So we talked about one of them earlier with the electroosmotic flow. That was the Coulombic interactions. You had some charges in the channel, and the electric field that you put across there was dragging those charges forward. There's also something called the polarization force, which is proportional to the gradient of the electric field. The dielectric force is proportional to the electric field squared, and the gradient in the dielectric permittivity. And then there's something called an electrostrictive force too, which is proportional to the gradient of the electric field squared. And I'm not aware of any devices off the top of my head that have used this type of pumping mechanism before. So the three common classes, the first one is the induction the induction electrohydrodynamic pump. This is where a charge is induced in a fluid by applying an AC voltage across an inhomogeneous fluid. So there's two fluids in here. And each one of these fluids has a different electrical permittivity or dielectric constant. This means that the fluids respond in different ways with respect to their electric fields. All right, so this charge induction, the fact that you have these two fluids here and they have different dielectric constants, when you put a voltage across there, when you put actually a lateral voltage, this creates positive and negative charges at the interface like this. If we look a little bit closer at this, you'll notice that there's a series of electrodes here, an array of electrodes. The positive voltage is connected to this one, this one, this one. So every three electrodes are alternating. So this is the positive voltage. The next one is ground, and then the next one is the negative voltage. It's positive, ground, negative. And it's positive, ground, negative, positive, ground, negative. So when you put a voltage between the positive and negative fluid, or positive and negative electrodes, it creates an electric field that looks something like this. I can write on here. The electric field is sort of goes like this. These are called fringing electric fields. So, when you have these electric fields and the electric field is going through two fluids that have different permittivities, there's some charge buildup at the interface between the two fluids. So that's how you get your positive and negative charges like this. These charges are then moved by activating the electrodes in a traveling wave configuration. So first you apply a positive voltage between these three electrodes. You apply the voltages between these three electrodes, and then you apply the voltages between the next three electrodes, and then between the next three electrodes. So the electric field is being moved from left to right in sequence. So these are called induction pumps. So this type of pump obviously requires two fluids of different dielectric permittivity. Not necessarily useful in biological assays, but it can be if you're just trying to pump some kind of like a heat exchanger liquid through a channel, for example. Maybe you don't care so much about what the dielectric properties are. You just need to pump some fluid through a channel to remove heat. In that case, something like this could possibly work. A lot of these electrohydrodynamic pumps are not really used too much in lab-on-a-chip type applications yet, at least in commercial ones. There have been some papers reported in the research areas, but they're interesting from just from a mechanistic standpoint. The next thing is the injection type pumps. Now, when we were talking about electro-osmotic flow, we generated these charges in the liquid just by virtue of the interactions of the liquid with the surface of the channel. Now here, what's happening is we're actually injecting charges into the liquid. So there's two things happening here. You have these electrodes, interdigitated electrodes, these are called. The bottom ones here, these are all the positive terminals, and this part here is all the negative terminal. When you apply a voltage there, it generates an electric field between these two. If the voltage is large enough, you can initiate an electrochemical reaction. That electrochemical reaction can induce charges in the working fluid. It injects ions into the bulk fluid. Now, once those ions are injected, the non-uniform fields that occur due to this non-uniform electrode geometry. Smaller electrodes tend to have larger electric fields than larger electrodes. Again, small electrodes have larger electric fields than large electrodes, so, or more uniform electrodes. As a result, there's a non-uniform force that propels these ions going forward from left to right. So those are the injection type pumps, and the polarization pumps rely on the dielectric force. So you have a non-homogeneous electric field. I'm sorry, a polarization. They rely on this polarization force. It relies on a gradient in the electric field. So if you have a liquid like this and you were to apply 2 electrodes in there and apply a voltage between the 2 electrodes, you're creating a non-homogeneous electric field. The electric field is very strong between these 2 metal plates, and it's less strong kind of on the outsides here. So the dipoles in this liquid, let's say this is a dielectric liquid and it has dipoles in it. The dipoles will move towards the high field regions. That's one way that you can use an electric field to actually pump liquid up into this channel. Okay. Now again, I'll just mention that these are all interesting from a scientific standpoint. They have not been implemented widely in practice, but nonetheless, I think they're pretty interesting. One last one I want to cover, the magnetohydrodynamic pumps. This relies on something called the Lorentz force. Does anyone remember Lorentz force from physics or electromagnetics? No one? Okay. It's been a while since we talked about electromagnetics, probably. So the Lorentz force is an electromagnetic force that affects moving charge. If you do like you can do a Wikipedia search on the Lorentz force, and you can learn more about that. Basically, if let's suppose Lorentz force. Have any of you heard of Hall effect sensors?
Yeah.
Hall sensors? Hall sensors are based on the Lorentz force. So what does a Hall sensor do?
So the ions will go like this arcway to the two sides of the sensor.
Mm-hmm.
So it will deplete on one side, and then they will create a voltage between the two sides.
Right. And what is a Hall sensor used for?
I forgot.
It's to sense it.
It can sense the longitude. Right.
And magnetic fields.
Yeah.
It's used to detect magnetic fields. But it's also used for semiconductor characterization, which is probably the context where you may have learned it. And you can use it to characterize the number of carriers in a semiconductor. But anyway, like Lorentz force is basically the deflection of a moving charge in the presence of a magnetic field. So let's say you have a positive charge like this, and the charge is moving this way. And you have a magnetic field. Okay, so let's say the magnetic field is pointing out of this paper. So this is your B. So the magnetic field is coming out of the board. So this particle will actually be deflected down this way due to the Lorentz force that's exerted on the particle. The direction of the Lorentz force will be this way. So the velocity of this particle is moving from left to right. So the V is going from left to right. The magnetic field is pointing pointing out of the board, and the resulting Lorentz force is pointing down like this. So as a result, the particle gets deflected if a magnetic field is present. So, some of these high energy subatomic particle experiments that are done, you know, in those big collider systems like the Hadron Collider, like sometimes those systems, they use like these very strong magnetic fields to deflect particles, and the basis of that is the Lorentz force. It's a very fundamental physical phenomena. The equation for it is relatively straightforward. It's F equals J cross B. J is the current density as a result of the moving charge. The cross product of that with, so this is the current density vector. B is the magnetic field vector, and then the force is the force vector. So this requires moving charge. The charge must be moving. So the way that this could be used in a microfluidic chip is, you can imagine if you have charges that are moving through a microfluidic channel. Those charges are moving with a certain velocity, right? So you have a velocity, and you have this moving charge represents J, a current density. So that charge is moving through the microfluidic channel. If you apply a magnet to it, all right, again, this magnet is being applied orthogonal to the direction of fluid flow. As a result, what happens is, oh, hold on, this setup is a little bit different. I'm sorry, this is a little confusing here. Let me rephrase this. You're actually using electrodes here to generate a current. So the ions are, you're generating a current between this electrode and this electrode. So there's a current flow going from the right side to the left side. So the ions are moving this way, from right to left. The magnetic field is pointed up. The resulting Lorentz force is causes the charges to deflect off in this direction. So that's what causes the fluid to flow through the channel like this. Does that make sense? The ions are traveling from this electrode on the right side of the channel to this side. So they're going moving this way. The magnetic field is orthogonal to it. The resulting Lorentz force is shown by these arrows here. So those ions are basically being dragged off in one direction due to the Lorentz force, and that causes this causes the flow phenomena to occur. Now, in terms of miniaturization will increase the current density. Just like, like a thin wire will have a larger current density than a tiny wire compared to a larger wire. Now, the performance is typically limited by the magnetic flux density. So it's more limited by the B term rather than the J term. If you put a permanent magnet, on the top and the bottom of the channel, aligning up the poles properly, you might get 1 Tesla, and if you use an electromagnetic, maybe 0.1 Tesla. So this is what limits, how much force you can get. So the flow rate doesn't necessarily scale favorably, and joule heating can be an issue. If you're trying to run a lot of current from this side to this side, you can start heating up the liquid, and that will cause some issues. The relationships for the pressure and the flow rate for a magnetohydrodynamic pump are pretty straightforward. The maximum pressure, assuming that the current and the magnetic field and the length of the channel, if they're all orthogonal to each other, that's when you get the maximum Lorentz force effect, and you get the maximum amount of pressure. It's equal to the current density multiplied by the electric field multiplied by the length of the channel. That's how much pressure you'll generate from one side to the other. Maximum flow rate, it scales as the dimension to the 4th power. Okay, so you can see that this doesn't scale very well. Anything to the larger the exponent is, the less significant it becomes at the microscale. So nonetheless, with appropriately sized channels, you can generate flows using magnetohydrodynamic pumps. but you have to be working with the correct types of fluids. And so you run into some of the same issues that you would with other types of electrohydrodynamic pumps. So just to wrap up this module then, the types of pumps that we talked about. One is based on mechanical displacement, mechanical movement, and the other one is based on, the dynamic micropumps are based on adding energy into the system. So in terms of like microscale devices, both are used. In fact, I would say the mechanical displacement pumps are used more frequently than some of these, the electrokinetic and the other dynamic sorts of pumps. This just should say, I would say, dynamic micropumps rather than electrokinetic. But these are some of the things that when you're selecting a micropump for a specific application, if you're thinking about mechanical displacement pumps, you have to consider the fact that bubbles will really cause issues in your system. If you need bidirectional capability, that's where mechanical displacement pumps fare very well. In some cases, they scale relatively okay. In other cases, they don't scale as well as electrokinetic pumps. When you're dealing with mechanical displacements, you can also do valving, you can generate constant pulsatile flow, and you have a bunch of different actuation mechanisms that you can choose from depending on your application. So we talked about PCTs, thermopneumatic, electrostatic, electromagnetic ways. These are all ways that you can actuate a diaphragm. When we talk about dynamic micropumps, one of the downsides is that they depend on fluid properties, but on the plus side, they can generate square flow profiles, which have less dispersion than the parabolic flow profiles. On the downside, you have the surface requirements. You have to ensure that your surface requirement is enough to generate a zeta potential in the case of electro-osmotic flow. These don't have any moving parts, so that's a big plus. It makes the system more reliable. These also have bidirectional capability. You do have to worry about how much back pressure that you can generate, how much flow rate you can generate when you're dealing with these types of dynamic micropumps. So the short of the story is this: there's no particular pump that's better than any other one. It's more about which pump is appropriate for a given application. Okay, and if you look at some of the, if you look through this Iverson's paper here, they do a comparison of the back pressure of various types of pumps, the flow rates of various pumps, and other people have done comparisons of micropumps as well. But one of the things you find by reading these papers, you see that there's actually, you're looking for trends and you don't necessarily find them. So there's no hard and fast rules that say like this type of pump is better than this other type of pump. Okay, there are certain characteristics that you can mention, but no like end-all be-all kind of rules. Like, for example, in this particular comparison, these are all in your notes, by the way. Some of the general conclusions that they drew were the fact that electroosmotic and PZT pumps, they're good for miniaturization. They have good flow rates and pressures. But electrostatic pumps, which electrostatic pumps offer, they have very small size and very good performance. Electrostatic pumps don't necessarily are you might think that because they have moving parts, they wouldn't operate as efficiently as electroosmotic or PZT-driven devices. But in fact, they do. And one of the advantages is that you can get decent performance because they can be actuated very rapidly. From the other side of things, like thermopneumatic devices that use heaters to heat up and cool down liquids, and thermopneumatics also to generate bubbles, those phase change-based micropumps, they generally have low performance, but they're less expensive to make. So these are all things that have to be considered. Cost, when one is making a micropump, the things that you want to consider is flow rate, back pressure, size of the pump, the power consumption, and material compatibility. Often you need a pump that's compatible with the process that you're working with. So from these graphs, you can also see something that the flow rate depends hugely on the size of the pump. The back pressures and flow rates that are generated in these pumps, in all three of these graphs, one of the basic things that happens is that the larger the pump is, the more flow rate it can handle. This makes sense, right? You know, if you make the pump larger, it can pump more fluid through there. In order to account for that, some of these graphs have actually normalized the flow rate. For example, this one, the max flow rate has been divided by the size of the pump to kind of account, to normalize for those differences. So if you're trying to compare apples to apples, for example. You know, nonetheless, you see you see huge variations in the amount of flow rate, the amount of pressure generation in these different types of pump modalities. So a lot of it is often dependent on which type of pump offers the most reliability and is most easily integrated into your process. So I mentioned some general trends here about the EOF and PZT pumps, electrostatic pneumatics. One other thing is that electroosmotic pumps can generate large amounts of pressure, as I mentioned earlier. This particular graph shows the micropump size on the x-axis and the self-pumping frequency. So this is the amount of time that it takes. How many pump volumes can it pump per minute? So whatever the volume of the pump is, how many of those volumes can be pushed through the pump per minute? So that's the self-pumping frequency. So as you can see that these different pumps appear really all over the map. In terms of the highest flow rate, this was an electro-osmotic pump. Okay, and you're reading these charts is a little bit tricky here, but you can see that along this line here, anything above here is 10 milliliters per minute. Things around here are around 1 ml per minute, and so on as you're moving down. So questions on micropumps? These are different applications of pumps. Besides the pumping around fluids for lab-on-a-chip type applications, they're used in vivo systems for insulin delivery. There's a growing interest in using them to cool down microprocessors. I'm sure you've seen that one of the issues with microprocessors in your computer right now is they get very hot. And companies like Google and Facebook, when they have their big server farms, they're very concerned about keeping their server temperatures down. Best way to cool something off is to douse a bunch of water on it, right? But obviously can't do that with the server, but there's been a lot of proposals to just beneath the microprocessor or within the microprocessor itself to have these integrated fluidic channels where you pump liquids through there to help keep the chip cool. And there's actually a lot of NSF money that went into that a few years back. I mentioned chemical biological analyses, cell sorting and flow cytometry, that falls into here. PCR pumps, fuel cells. Hydrogen fuel cells were proposed as alternatives to lithium-ion batteries. Fuel cells require some type of pumping mechanism. DNA hybridization, these are all falling into chemical and biological analyses. So there's many different applications of these devices. And if you're interested in learning more, this is a decent article, review article on micropumps. This is also one. These are the two well-known review articles. And there are more recent ones too. A lot of the more recent review articles are on specific micropumps for specific applications. The one that's used most often in biological or microtast type systems are the Quake, the Quake valves and the electroosmotic ones. So we'll end this module here, and we can get into talking about the separation, chemical separations. So let me